Hi, in this video I'll explain about the fundamental of a magnetic field that's set up when we pass a current through a wire or a long conductor. In a bar magnet, we don't need to pass a current to get magnetism. It has a field of its own. When we pass current through an electric wire, it behaves like a bar magnet and sets up its own magnetic field. When the current is switched off, the magnetic field is switched off too. Let's look at an animation. So take a battery, you have a positive and negative terminal connected through wires to a long straight wire which is red in color over there, and the current returns back to the negative terminal. You can see a pink arrow that's moving all over the place. That's to indicate the direction of the electric current flow. And the yellow rings are the magnetic field lines that are set up as a result of the current flow. The little green arrows show the direction of the magnetic field. So the rings constitute a surface that's perpendicular to the wire, and they're concentric. You can see that none of the rings of magnetic field are intersecting each other, just like in a bar magnet. The little green arrow on the left shows the direction of the magnetic field at that point on that circle. The green arrows do not indicate that the magnetic field is rotating. The magnetic field is static. The green arrows at different points on the circle are tangents to the circle at the various points. So please consider it as the varying direction of the magnetic field vector at different points on the circle. You can also see that there are several rings. There are infinite rings, in fact, and I have drawn only a few of them. Otherwise they would be very crowded. At this point, let us introduce the right hand thumb rule. You can see a right hand there. The direction of the thumb is same as the direction of the current. You can see the pink arrow just next to the hand. The fingers are curled around the wire and the nails are pointing upwards. So you can see that at below the circle, the arrows are horizontal. It's same as the direction of the fingers. On the outside of the fingers, or the edge of the fingers, nails are pointing upwards, and the ring that you see at the edge of that red wire, you can see that the green arrow indicates the direction of the magnetic field that's pointing upwards. At every point of the magnetic field, it will follow the right hand thumb rule. On the inside of the wire, the hand is of course pointing downwards, so the magnetic field green arrows are all pointing downwards. This is only to elaborate the directions at various points. Let's look at another animation. You can move the right hand throughout the length of the wire, and at every given point it will give you the direction of the magnetic field or the direction of the current. So looking at it from behind the current, the direction is clockwise. You can see the summary here of what we saw in the last few minutes. The magnetic field strength is what will be asked in numericals, and this is expressed in terms of a symbol called B, although H is also used. Let's look at a real life numerical. So the magnetic field for the case of a long straight wire is defined as mu0 into the current divided by 2 pi r, where r is the distance of a given point from that wire. Obviously, if we are standing very far away from the wire, we will experience a very small magnetic field, just like if we keep a bar magnet very far away from us. So B is proportional to the current. More the current, stronger the magnetic field. That sounds logical. Farther away, less of the magnetic field. So let's apply that to a real life problem. We have a current of 10 amperes flowing, and we have to find the magnetic field at a distance of 0.1 meters away from the central axis of the wire. So plug in into that equation and we find B is equal to 2 into 10 to the power minus 5 teslas. The mu0 here is a magnetic permeability, 4 pi into 10 to the power minus 7, and is a constant for space, the universe, and for Earth itself. It's the magnetic permeability in vacuum. I hope this presentation was useful in understanding the basic concept of magnetic field around a current carrying conductor. Thank you very much and have a great day.